Okay, so today what we are going to speak about is Lewis structure. Okay, so in order to write or draw a component, a compound, we need to know the Lewis structure. Okay, because he has given certain rules. Following his rules, we can assume the structure of compound. Okay, so we'll see what are the rules and things, right? So the first thing is to identify the central atom and the surrounding atoms, right? So if a given compound, first we have to see which atom would come into central, and then which other atoms are in the surroundings, right? So in order to identify the central atom, you need to make sure that the atom should form multi bonds, more than single bonds, right? So if you take oxygen, it can form more than one bond. Single bond also possible, double bond also possible, right? But if you take hydrogen, it cannot form any multi bonds, right? It can form only single bond. So also that you have to make sure that the electronegativity should be less than comparatively with the other atoms. When you are placing a central atom, that atom should have less electronegative than the others, right? So this is the main thing that you identify the central atom, right? So then you have to calculate the total number of electrons for a given chemical formula, considering all electrons in the valence shell of each atom, right? So let's say this is H2O, water molecule, right? We have two hydrogen atoms and then one oxygen atom, right? In hydrogen, you have one valence electron, so there are two atoms, so 1 into 2, 2. There are 6 valence electron, only one atom is there, so 2 plus 6, 8. 8 valence electron in total, right? So calculating the total number of electrons for a given chemical formula, considering all electrons in the valence shell of each atom, right? So H2O, oxygen atom, contributes 6 electrons and 1 electron from each hydrogen atom, and then 6 electrons from oxygen atom. All together there are 8 valence electrons, right, present in H2O molecule. So if it is a negatively charged ion, then negative charges should be counted as well. In that sense, if it is an ion, when you are comparing, let me say NO2 minus, CO3 2 minus, right? It's a negative ion. What you need to do is you have to count the negative charges. Let me say NO2 minus, with these valence electron, you have to count 1 electron, right? If it is a CO3 2 minus, you have to count C plus 3 oxygen atom valence electron plus 2 electron together, because negative ion means we are like gaining the electrons, right? So then that we have to add. If it is a positive ion, vice versa, you have to subtract the electron, right? So let me say NH4 plus, you have to count N plus 4 hydrogen, then you have to subtract 1 electron, right? So that is how you have to make the complete number of electrons, right? So if the ion is positively charged, then the equivalent number is deducted from the total valence electron. So NH4 plus ion, that is how they are coming to the same, okay? So third one, a bond is denoted by a pair of dots between the central atom and the surrounding atom. Each surrounding atom is connected to the central atom with at least one bond. In that sense, if you are drawing the when you start to draw the structure, first you have to come up with the single bonds, then only you have to put the other bonds, like it's a double or triple bond, whatever it will be later on. Okay, so first you have to connect with the single bond. Bonding electron pairs are denoted first as a pair of dots. Lewis dot diagram we have already studied, right? Or a short line. So one short line. So the line represents 2 electrons from both atoms, right? I have already talked about it. So the drawn between central atom and each of the surrounding atoms. Next, the remaining electrons are distributed starting from the most electronegative atom to complete the octet. In that sense, like when you're like putting the other electron, I'll draw it and show you. When you're completing the other electrons, first you have to put the electrons to the highly electronegative atom. Then only you have to put it for the less electronegative atom, right? So starting from the most electronegative atom to complete the octet, each electron pair is marked by a pair of dots, lone pair electrons. If the electronegative atoms are surrounding atoms, then lone pair are marked on the surrounding atoms in order to complete the octet of each atom. CCl4 is an example. So, if you see H2O, oxygen and hydrogen, right? So this is H2O, right? First I connected with a single bond. So in total how many electrons are there? Actually before I draw the diagram, you have to count the electrons. So here 2 plus 6, 8. 8 valence electrons are there. Okay. So now oxygen and hydrogen. Okay. So I connected with one single bond. So means there are 2 electrons, here also 2 electrons. No? So 8 minus 4. Right? 2 plus 2, 4. 4 electrons are subtracted from this total electrons. Right? So then that will be remaining number is 4. Right? So 4 electrons you have to complete. Now remaining, you got it. Got it, right? So 8 electrons in total valence. Here in the bonds you put one bond here and then one bond here. In that sense 2 electrons plus 2 electrons, 4 electrons. So you have to reduce 4 electrons from the total valence number, right? So the remaining will be 4. That 4 electron you have to put it for which atom?
Same.
Highly electronegative atom, right? So which is the highly electronegative atom here?
Same.
Oxygen, right? So first 2, 4. Now 2, 4, 6, 8. So the octet is completed. For hydrogen, we have 2 atoms. Octet is completed now. Here also hydrogen, there are 2 atoms. Octet is completed, right? Hope you understood. See CCl4, you have carbon and 4 chlorines, right? So for chlorine you have 7 electrons, whereas carbon there are 4 electrons. There are 4 chlorines now. So 7 into 4, 28 plus 4, 32. So in total you have 32 electrons. So valence electrons, right? 32 valence electrons. So when you are drawing it, first you have to put single bonds, right? So there are 4 chlorine atoms surrounding carbon atom. So carbon will be placed in the middle because less electronegative than chlorine. So it makes 4 bonds. So if you put 4, there will be 8 electrons reduced from the 32 electrons, right? So the remaining electrons you have to put it for chlorine because chlorine is the most electronegative atom, right? So this is how we draw the Lewis structure. So see the way they place the atoms. M double bond L means single bond. So M dot L in the sense it is single bond, and double bond in that way it will be shown, and triple bond dative bond, right? Dative bond shown like this. So if electron pairs are remaining after distributing electrons pairs on the surrounding atoms satisfying the octet rule, then leftover pairs of electrons are marked on the central atom. Got it? Now, if you take PCl3, how many electrons are there in the phosphorus? 5, right? So chlorine 7. There are 3 chlorine. So I'll draw it and show. If you see PCl3, there are 5 electrons in the chlorine, sorry, phosphorus, and 3 into 7 electrons in chlorine, right? So 5 plus 3 into 7, 21. So 26 in total. Okay, so there are 26 total number of valence electrons, right? So when you're drawing it, okay, now there are 3 bonds between 3 atoms, right? So we'll distribute the electrons first. So 26 in total, but here there are 3 bonds. So 2 plus 2 plus 2, in that sense 6. So we have to reduce 6 electrons. Then remaining will be 20. We have to put 20 electrons, or we have to distribute and give. So first, whom to give the electrons?
Central.
No, wrong. First, whom to give the electrons?
Side electrons.
Most electronegative atom,
negative
right?
atoms,
So
yeah.
which one is the most electronegative
Chlorine.
atom here?
Chlorine.
So we have to give it to chlorine. So 20 of how many electrons are there in chlorine? 7.
Yes.
Plus 2, right? Here 2, then 5. No, 6. Here 2 to be 6. Then you know octet.
6, yes.
Okay, now 2, 4, 6, 8, 10, 12, 14, 16, 18. So 18 electrons are distributed. Now this is octet. This completes its octet rule, right? So this is 8 electrons are there, right? More than that you can't put. So now remaining 2 electrons are there now. Altogether 26. There are 3 bonds. So 6 left over, right? So the 20 will be leave. From that 20, I put the the chlorine atoms, right? So from that we have 2 remaining electrons, right? So that 2 remaining electrons will be placed in central atom. Okay, this is how we draw the structure. Because this is very important part, drawing the Lewis structure. Like, if you know this, half of the chemistry is fine. That's right. Okay, coming back to the rules. The next one, after distributing all the electron pairs, the number of electrons on each atom should be compared with the number of electrons in the non-bonded state of the atom, like free atoms. The remaining ones we put, right? To assign the formal charge and then check the completion of the octet. So in that case of a bond, 1 electron is counted for each atom, and if lone pairs are present, both electrons are counted to the particular atom. Priority is given for completion of the octet. For an example, NH2 minus ion, right? If you see NH2 minus ion, so when you compare to nitrogen, NH2 minus ion, NH2 minus, right? So 1 nitrogen plus 2 hydrogen atoms, right? Plus a charge, negative charge. So there are 5 electrons in the outermost shell of nitrogen, plus 2 plus 1. This 1 electron is placed because of the negative charge. Okay, so there will be 8 electrons in total. If you draw NH2, first we have to put 2 bonds, right? So then that means 4 electrons are removed, right? So then remaining number is 4. So that will be placed in nitrogen, right? So now when you count it, 2, 4, plus 2, plus 2, there will be 8 electrons, right? But you all know that nitrogen has only 5 electrons in the outermost shell, right? But here in this case, it has become 6 electrons, right? 2, 4, here also both 2 electrons, right? So then that means 6 electrons for nitrogen itself. So that 6 electron is because nitrogen atom has gained one more electron. So that is because it becomes 6 electron, right? So you put a charge over here. That charge represents nitrogen atom has received one more electron, right? So this is how NH2 minus structure is represented as. Okay, now the next law of the rule. Electron distribution shall be rearranged in order to minimize the formal charge on atoms and completion of octet by converting lone pair of electrons to bonding pair of electrons. So if you see SO3 2 minus, SO3 2 minus, how many electrons for sulfur? 6 proof, no? 6. Oxygen 3 into 6 plus 2 electrons. Why? 2 minus, no? So then that means 2. How much? 6 plus 18 plus 2, 20, 26. Okay? So there will be 26 formal valence electrons. So that is what they said in that diagram, right? So S O O O, right? There are 3 oxygens. First you put 1 bomb, right? So now what you have to do? You have to check the remaining number of electrons. 26. How many electrons are bonded now? 6 electrons, right? 3 pairs of single bonds. So that means you have to remove 6 electrons. There will be 20 more electrons, right? So which one is the most electronegative atom here? Oxygen, right? So we have to place the electrons in the oxygen atoms, right? So how many electrons?
Sir, oxygen or oxygen?
Oxygen. How many electrons? 20, right? 20 electron means 2, 4, 6, 8, 10, 12. Then 14, 16, 18. Now, see how many electrons? 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. There are 6 electrons. Sorry, there are 8 electrons in the oxygen, right? So now, the remaining number is there, no? How many are remaining?
2.
2. That will be placed here, right? So if you put that, now how many electrons are there in sulfur? 6, right? Originally 6.
Yeah,
Now
5.
1, 2, 3, 4, 5. Right? So that means what had happened there?
1 electron.
1 electron is lost. Okay. Originally, how many electrons are there in oxygen?
8.
8.
Originally
6.
6. Now 2, 4, 6. Here also 1. This bond represents 1 electron from oxygen and the other electron from the sulfur, right? So here also 1. So then that means 7.
Yeah,
You got it?
Yes, yes.
7 electrons are there in oxygen now. Means it had received 1 electron from the other atom, right? So there should be 1
Minus.
minus. Good. Here also the same, no?
Yes.
2, 4, 6 plus 1, 7. So that means 1 minus is there. Here also 2, 4, 6 plus 1, then that means 7. 1 minus is there. Here it should be 6 in original atom, but 2, 1, 2, 3. So altogether 5, right? So 5 electrons only there now, right? So means it has removed 1 electron. So then there should be a plus formation. You got it? The formal charge. Here 1 plus, here 1 minus, here 1 minus, here 1 minus. Right? Now what is the formal charge then? See, 1 minus 1 minus 1 minus 1 plus. 3 minuses are there, right? So 1 plus is there. So 1 plus and 1 minus can cancel the charge, right? So the remaining is what?
Minus.
2 minus.
Minus.
That is why we put SO3 minus. Got it? Did you draw this? CO3 2 minus. Can you draw for this? First what you need to do?
Carbon, draw the carbon.
Electron number.
Yes.
Oh, yeah, electron number.
Carbon.
Carbon
Carbon is
4
4.
plus oxygen
6. 3
6
into
3. How much?
18
plus
plus 2.
2.
24.
20 24. Carbon,
Carbon, oxygen,
oxygen, oxygen, oxygen. Right? There are 3 oxygen. First we put the single bonds. Right? Then we have to do what? We have to
separated.
reduce the number of bond pairs. Right? So 24 minus 6. How much?
80.
80. So now we have to distribute the 18
18
electrons
electrons.
first. 18, 2,
2,
4, 6, 8,
10.
10,
12,
12, 14,
14.
16,
16.
6,
18.
16,
80.
80. Now 1, 2, 4, 6. 2, 4, 6. There should be 2 more electrons, right? CO3 2 minus, we have double bonds.
Yeah, that's a double bond.
So you have to draw
one more oxygen.
But we should, there should be
Reduce.
3 oxygen.
Right.
now see the 2, 4, 6, 2, 4, 6. How many remaining? There is a double bond, okay? So 1, 2, 3, 4. 4 bond pairs means 8 electrons. You have to reduce 8 electrons from 24, right? So how much?
8 and 16.
16, right? Now 16. You have to distribute the 16 electrons from this one. Now carbon is completed anyway.
Yeah.
So you have to anyway consider the oxygen, right? 16, no?
Yeah.
8. 2, 4,
6,
6, 8,
10,
10,
12,
12, 14, 16. Okay? Now, in oxygen you have 2 plus 2 plus 4. Sorry, 2 plus 2 plus 2. Here 1, right? So, altogether 6 electrons. So, no issues. Here, 2 plus 2 plus 2, 6 plus 1 means 1 additional, right? So, you have a negative charge here. 2 plus 2 plus 2, 6, 7, right? 1 additional charge, right? So 2 charges are there. So this is CO3 2 minus.
minus.
Got it?
Yeah.
Should I erase it?
Yeah.
Can you do for NO3 minus? NO3 minus. For nitrogen, 5. Oxygen,
Oxygen, 6.
6 into
3,
3, 18 plus 1. Right? 6 plus 18,
24.
24. Nitrogen, oxygen, oxygen, oxygen. Right? First you have to put single bonds. Right? So then 6, you have to remove 6. So there are the 18 electrons. So now we have to put 18 electrons in total. Right? First to oxygen. 18, 2, 4, 6, 8, 10,
12,
12, 14,
16,
16,
18.
18. Now total 18 given. Right? So again oxygen have one negative charge. Here also oxygen have
Negative
one
charge.
negative charge. Here also oxygen have one negative charge. If you see nitrogen, there will be one electron, one electron, one electron. Right? So in the outermost shell you have only 3. But originally have 5 electrons. Right? So what had happened there then? 2 electrons are lost. Right? So that means plus 2. So now 1 negative, 1 plus cancel. 1 negative, 1 plus cancel. So the remaining is what? 1
Minus.
negative. This one is remaining. So then that means NO3 minus. Okay? Hope you are understood. You got it?
Yeah.
Okay. So in NO3 minus, if you see, this is the structure of NO3 minus, right? But this structure, you have seen one negative charge, here 2, here 1, here 1, right? This is the formal charges are given, right? But the structure is okay, but this is not stabilized, right? So this kind of a structure is not common in nature, right? So they always tend to stabilize the structure, right? So the formal charges are distributed between the atoms, but still not, the stability is not commenced, right? So what happens is, these two, they form a double bond between them, between these two charges, okay? So they make the double bond. So now, ultimately, they become what? Stable, right? See, 2, 4 plus 4, 8.
8.
Here, 2, 4, 6, 8. Here, anyway, there is a charge. So these two charges will be, cancelled. Now, NO3 minus is stable with double bond, right? Cancel. Okay, next one. All atoms of Lewis dot structure have satisfied the octet, but it is not stable since it has maximum formal charge distribution. Hence, the lone pair of electrons are rearranged in order to obtain the stable Lewis structure having minimum formal charge distribution. The following sketch shows the way of rearrangement. So, if you see SO3 2 minus, right? SO3 2 minus. So, SO3 2 minus, 1 sulfur atom and 3 oxygen atom, 2 negative charges, right? So, see the way they arrange the formal charges, right? Finally, the Lewis dot structure Lewis dot dash structure for SO3 2 minus is given as below. So what happens is, when you are drawing it, if you put only single bonds, they are not stable. Okay. So like earlier when you are drawing CO3 2 minus, actually the single bonds are not that stable in that component. Okay. So we have to put one double bond, right, in order to make the component stable. So the same will happen here also, right? So see, one double bond, one single bond, sorry, 2 single bonds. So they distribute the charges, right? So this structure is comparatively more stable than the above, right? So when you are making the double bond, that charge also cancel. Now, see, there is a negative charge, but when you are making it as a double bond, that one cancels, right? So then they become, that is why they become more stable. These are some of the structures: CO2, POCl3, HCl, NO2 minus, NO3 minus, and then NO3 plus. Sorry. NO2 minus, NO3 minus, NO2 plus. So the when you are drawing the NO3 minus also, like there is a double bond. Okay. So in order to stabilize it, you have to put the double bond. Okay. Now in a summary, what are the rules you have to follow? First, you have to write the molecular formula, right, of a given component, and then you have to draw the atom placement, right, and then you have to do the single bonds, right. Then you have to impose the octet rule, right. Finally, you can come up with the Lewis dot diagram, right. So, Lewis dot structure of NF3. You can draw, right? These are some of the examples. And CCl2F2. Okay, the central themes of valence bond theory. Right here, what we are going to talk about is the hybridization. Okay, so what do you mean by hybridization? Have you seen car called hybrids or the watermelon?
Yeah.
Hybrid ones. What do you mean by hybrids? Hybridization or hybrid means what? What is a hybrid car?
Hybrid cars.
What are hybrid cars? Usually the electric power ones, like they can run by fuel as well as the electric power battery. Both are there. Both can support, right? So hybrid means kind of a mixture. You mix something and you get you mix two and then you get something new. Okay, that is hybridization, kind of mixing. So the basic principle, a covalent bond forms when the orbitals of two atoms overlap and are occupied by a pair of electrons that have the highest probability of being located between the nuclei. Right? So three central themes: a set of overlapping orbitals has a maximum of 2 electrons that must have opposite spins. That we have already studied in the atomic theorems, right? In the orbital, both electrons should spin opposite side, right? Then only they can two together. The greater the orbital overlap, the stronger, more stable the bond. Like in order to make a bond, they have to overlap and they have to make hybrid. Okay? So the valence atomic orbitals in a molecule are different forms. Those in isolated atoms are called hybridization. Right? So now let me say there are two atoms, they make a bond. Right?
Yeah.
First they have to hybridize. So then they will come to a common energy state. Then only they can make the bonds. Right? That is hybridization. I'm not going much on this. I'll just give you the very basic, right? So, see, hydrogen. What is the electron configuration of hydrogen?
2.
1 is 1, right? In order to stabilize, what it has to be? 1 is 2, right? We have studied 2 hydrogen, they make the bond, right? See, 1s means 1. So the s orbital is what? Pair, right? Can you remember? S orbital is pair, p orbital is dumbbell shape, right?
Dumbbell shape.
So, see, 2 s orbitals are hybridized into this particular shape. So now they have the bonding. This is how actually they make the bond. See, orbital overlap and spin pairing in 3 diatomic molecules, right? So this is how they make the bonding. This one, what do you call? This is a s orbital, and this one is a p orbital, right? So they both hybridize, and they make sp hybridization. Like hybridization, also you have different types. sp hybridization, sp2 hybridization, spd hybridization. Like according to the orbitals, they are different. Okay. So in fluorine molecule, this is HF molecule, S and P hybridization. Whereas fluorine molecule, we have 2 p orbital, right? So those p orbitals are hybridized. So this is p hybridization. Okay, Linus Pauling proposed that the valence atomic orbitals in the molecules are different from those in the isolated atoms, right? So the mixing of certain combination of atomic orbitals generates new atomic orbitals. In that sense, like now s orbital and p orbital are both are separated, right? But when you are mixing up together, they form one particular orbital called sp hybridized orbital. Okay, like that. So the process of orbital mixing is known as hybridization or generates hybrid orbitals. So hybridization means simply what I just wanted to give you the idea. Hybridization means mixing of orbitals. That's all, right? See the key points. The number of hybrid orbitals obtained equals the number of atomic orbitals mixed. So the number of orbitals you mix. So let me say 1s and 1p mixed. Then how many orbitals are formed? 2 orbitals. sp orbital, right? So the type of hybrid orbitals obtained varies with the types of atomic orbitals mixed. So types of hybrid orbitals: sp2. sp2 means what? 1
is
s and 2 p orbitals. sp3
1
1
s
s
and
and
3.
3 p orbitals. sp3d 1 s 3 p orbitals 1 d orbital. sp3d2, right, means 1 s 3 p orbitals and then 2 d orbitals. How many hybrid orbitals are formed when sp3 hybridization occurs?
4.
4. How many are present in sp3d2 forms?
6.
Right? Okay. Refer means what? You have to go through and you have to make a note on this. Okay? Vesper, valence, shell, electron pair repulsion theory. Right? Vesper theory means there are like amount of rules. You have to go through them and you have to find out what in Vesper theory. The structure of the molecule. Okay, you are finding the structure.
Is it a homework?
Yeah, this can be homework, or maybe I might give you an exam on this or whatever. That's up to you. Okay, no homework, so you have to go through this. Hybridization. I was talking about hybridization here, but I just gave you the idea what is hybridization. Okay, I'm not going through in detail. So what you need to do is you have to go through and get some notes. Okay, and clarify that. And resonance. Resonance also the same. When you're drawing the structure, they they tend to move stabilized, right? So in resonance, more stability is there. So that is how the resonance works. So we have to go through that task. Okay, so the molecular orbitals, when two atoms combine, this model assumes that they are atomic orbitals overlap to produce molecular orbitals, or orbitals that apply to the entire molecule. So in some ways, atomic orbitals and molecular orbitals are similar. So usually this is not a big thing, okay? Atomic orbital and molecular orbital. When molecules are formed, then they make molecular orbitals, right? So hybridized and they make the molecular orbital. So when atoms are considered, then they are like atomic orbitals. Like we studied this atomic theories and all that, right? So those are atomic things. Same thing, similar thing. When you are comparing to a molecule, they make hybridization and all that. So they make
molecular orbitals.
Okay, just as an atomic orbital belongs to a particular atom, molecular orbital belongs to a molecule as a whole. Like if you take CO2, both they consider the molecular orbitals. So a molecular orbital that can be occupied by two electrons of a covalent bond is called bonding orbital, right? So when they are combined with covalent bond, they are bonding orbitals. Okay, so sigma bond, when two atomic orbitals combine to form a molecular orbital that is symmetrical around the axis connecting two atomic nuclei, is sigma bond. A symbol of sigma bond is this. So what is sigma bond according to you? See, s orbital. Any atom, you consider any atom, but they are s orbital, and the other one's s orbital. Let me say hydrogen. Okay, so you have a nucleus, right? Directly within this nucleus, you make the bond, right? So the attraction is between the nucleus. Nucleus and this. So this is sigma bond, more stronger. This is what we call as single bond. Till now we studied about single bond, double bond, all that, right? So this sigma bond represents the single bond thing. Usually we put the single bond first, no? Right? Then only in a double bond, right? That is because these are more strong. Sigma bond in general, covalent bonding results from an imbalance between the attraction and repulsion of the nuclei and electrons involved. So the nuclei and electrons attract each other. Nuclei repel other nuclei. Like when two nucleus come together, they repel, right? Because same charges. But electrons repel other electrons. Again the same charges, but electron and the nuclei, they attract, right? In bonding, nuclear orbital of hydrogen, however, the attractions between hydrogen nuclei and the electrons are stronger than the repulsions. So, like when you consider the repulsions also there, but still the electrons and the nuclei attraction is more stronger than the repulsion. So the balance of all the interactions between the hydrogen atoms is thus tipped in favor of holding the atoms together. Right? So the result is a stable diatomic molecule of H2. This is how they make the sigma bond. Right? So there is a repulsion. What are the repulsion? Electron repulsion is there. Nuclear repulsion is there. Right? But still they are stabilized because the electron and the nuclei attraction is more powerful than those repulsions. Right? So they stabilize and they make the diatomic molecule. Okay, sigma bonds between p orbitals. Atomic p orbitals can also overlap to form molecular orbitals, right? We saw that earlier also, no? That F2 molecule, that is p orbital overlapping, right? So fluorine F2 molecule, for an example, has half filled 2p orbital, right? So when two fluorine atoms combine, the p orbitals overlap to produce a bonding molecular orbital. So when they make the overlapping, that is called bonding orbital, right? So there is a high probability of finding a pair of electrons between the positively charged nuclei of the two fluorides. The overlap of the 2p orbital produces a bonding molecular orbital that is symmetrical when viewed around the FF bond axis connecting to the nuclei. So therefore FF bond is a sigma bond, usually a single bond. Pi bonds. So what are pi bonds now? Overlap means only. What are pi bonds now? Sigma bonds are the single bonds, right? H. This is a sigma bond. CO2, C double bond O, C double bond O, right? CO2. One sigma bond, one pi bond. Pi bond means sideways. They make the bonding sideways, right? In the sigma bond of the fluorine molecule, the p atomic orbitals overlap end to end. In some molecules, however, orbitals can overlap side to side. See, when these two are bonded, that is sigma bond, end to end. But when these sides are bonded, then they are pi bonds. As shown here, the side-by-side overlap of atomic p orbitals produces what are called pi molecular orbitals. So the double bonds and the triple bonds are pi bonds. Single bonds are sigma bonds, right? Remember that. So the pi bond, in the pi bond symbolized by Greek letter pi, the bonding electrons are most likely to be found in oblong shaped regions above and below the bond axis of the bonded atoms, because atomic orbitals in pi bonding overlap less than in sigma bonding. Pi bonds tend to be weaker than sigma bonds. Remember, pi bonds are weaker than sigma bonds. That means double bond is weaker than single bond. Triple bond is weaker than double bond, right? So the bond energy goes down. Okay, when you are listening to it, you might think double bonds are more stronger, triple bonds are stronger than that, but not like that. Okay, because they are side to side connection, they can be easily broken up. Okay. See the attraction of electron and the nucleus, repulsion of two nucleus, repulsion of two electrons. Okay, attraction and repulsion both are together. This is how they make the bond pair. Okay, earlier I told that there are repulsion and attraction both, right? So this is how they stabilize. Both are there.
Repulsion below attraction or
Okay, now properties of covalent bonds. Okay, because of the covalent bond, what are the properties it gains? So the bond energy, bond enthalpy or bond strength. Enthalpy is again energy, right? Bond strength, the energy required to overcome the mutual attraction between the bonded nuclei and the shared electron. Bond breakage is an endothermic process. Bond energy is always positive. So bond breakage, what do you mean by bond breakage now? In order to reduce break the bond, right? Bond breakage is endothermic. Bond formation is an exothermic process, right? So when they form, that is formation. Bond length. For a given pair of atoms, a higher bond order results in a shorter bond length and a higher bond energy. A shorter bond is a stronger bond. Shorter bond is a stronger bond. So the bond length also, when the bond length reduces, their strength is increases. Okay? Because they are more attractive. See, they are given the bond energy of multiple bonds. Single bonds and multiple bonds, both are there. See the bond length, carbon 154 picometer, carbon double bond 134, carbon triple bond 121. So the see they have become shorter, right? Bond length and covalent radius. There are some questions given. Okay, weak forces between molecules, not the strong covalent bonds within each molecule. So are responsible for the physical and this one we are kind of talking about this intramolecular forces. Sorry, intermolecular forces. Okay, so we'll do that in the next lecture. Intermolecular forces. Covalent compounds are relatively low melting and boiling points. Remember, ionic bonds are higher melting point and higher boiling point. Right? So most covalent compounds are poor electrical conductors. Usually they are poor electrical conductors, right? Because they are not ionized in the aqueous state, right? Network covalent solids. No separate molecules held together by covalent bonds that extend throughout the sample. Quartz and diamond. So this network covalent solids, like diamond, quartz and all, like that is a shape, right? So that shape repeats. So they held together. So that is how they make high melting point and boiling point, right? So these example illustrates the strength of covalent bonds. Like because of the network solids, networking, they have more energy, so they make more melting points, right, and boiling points. See how they are like bonded quartz. This is diamond. So the carbon atoms. Electronegativity. I think you are okay with electronegativity, no? What is electronegativity and all that? I'm not going to repeat it. Change in electronegativity. Okay, hope you all know about electronegativity, right? So here we are going to talk about polar covalent bond and bond polarity. So what do you mean by polar? What is polarity? What is polarity? Now if you have hydrogen, two atoms shared, two electrons are shared, right? So this is equal distribution or different distribution?
Equal.
Why?
They are same atom.
Electronegativity, right? So they share same number of
electrons.
sorry, the same amount of energy
in
to hold this bond. right? Covalent bonds are involving atoms with different electronegativities generate partial positive and partial negative charges defined as polar covalent bonds. But if you take chlorine and hydrogen, this one have different electronegativity, right? So what happens? They attract the bond pair toward the chlorine, right? Because chlorine has more electronegativity, right? It can attract the bond pair. So what happens? Gets a slight amount of negative charge, whereas this one gives slight amount of positive charge. Okay, this is called polarity. Polar covalent bond depicted by a polar arrow that points toward the negative pole. So H2, F2 examples of non-polar covalent bonds. Okay, you can see there. Polar covalent bonding occurs when atoms are not different enough to transfer electrons, but at the same time not identical and cannot share electrons equally. Instead, there is an unequal sharing of electrons. So polarity is about unequal sharing of electrons, right? So when HF, which has an unequal charge distribution or partial charge, electrons are more attracted to or want to spend more time with fluorine than hydrogen. So this is what we call bond polarity, right? So the partial charge is represented by a delta, and here like this delta. And a positive negative sign depending on where electrons are positioned. Here delta charge means not positive or not negative. When you put plus and minus ionic charge, you can't compare that to here. Okay, positive means complete ion, but delta or plus means they are like kind of induced charge. It's a very little bit charge. That one positive charge you have to divide by 1000 or million times, then part of that, okay, that much a small amount of charge is represented here. Bond polarity and dipole moments. A dipole moment indicates the direction of charge distribution between two atoms can be represented by a center of positive charge and the center of negative charge. A dipole character of a molecule is often represented by an arrow which points toward the negative center and its tail indicated the positive center, like this. Any diatomic molecule that has a polar bond has a dipole moment. Dipole moment means like usually where the charge is, like you are indicating the direction. Okay. Now if you see X here, like kind of one part is positive, the other part is kind of negative. It's not complete positive or negative, induced charge, right? So this is what dipole moment. Okay, hope this is clear. Okay, that is not right one. Bond polarity. Ionic bonds are more polar than the polar covalent than the non-polar covalent, right? So okay, how to identify whether they are polar or non-polar or ionic? There is a small table, okay, you have to remember this. When electronegativity is lesser than greater than 1.7, then that means they are ionic. Difference between two atoms, you have to get the difference. When the polarity means 0.4 to 1.7, between that range, usually considered as polar covalent. They are covalent, but they are polar. Less than 0.4, they are considered as covalent. But less than, like around 0 means H2, you get the difference 0. F2, you get the difference 0. O2, you get the difference 0. Right? N2, again the difference is 0. Right? They are non-polar covalent. So they are completely covalent, 100% what? Covalent. But can ionic bond become 100% ionic? No. There is a percentage of ionic, right? But covalent bond can be 100% covalent. Why? They can form 0 difference of electronegativity atoms. Okay. So boundary ranges for classifying the ionic character of chemical bonds. You can see this diagrams. See, lithium fluoride is ionic bond, okay, ionic compound. So the charge distribution. So no bond has 100% ionic character, but 100% covalent character is there. Okay, electron sharing occurs to some extent. Refer again. There is a homework. Okay. Polarizing the power of cations, polarizability of anion. Like polarizing the power of cation means it's kind of inducing the power. Like you have a positive charge where you can like induce the charge of the other, right? So that is polarizing the power of cations. You have to go through that and get ready and say. Okay, ionic to covalent bonding continuum across the period. So, consider bonding between a metal and non-metal in period 3. Okay. Third period, what are the atoms are there? Sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. Right? So, see they are bonding. They are metal to non-metal, no? See they are bonding. Sodium chloride is what? Ionic.
Right.
Magnesium chloride?
Ionic.
Ionic. Aluminium chloride?
Ionic.
No, metal.
No.
Non-metal. Ionic.
Silicon chloride? Covalent.
Covalent.
PCl3 covalent. AlCl3 also covalent.
Yeah. AlC.
H2Cl2 also covalent. Cl2 covalent. Alright? So increasing the covalent character, decreasing the ionic character of NaCl2, Cl2. Okay. So underlying factor is electronegativity becomes smaller, the bond becomes more covalent. Like electronegativity becomes smaller means the difference become higher, no? So they become
More covalent.
like with the period that goes smaller, right? See the chlorides NaCl. The first one is NaCl powder, magnesium chloride powder, AlCl3 powder, silicon chloride, again PCl3, they become liquidized, H2Cl2 and Cl2 is a gas. So solid to gas, solid and then become liquid and then gas. aluminum chloride. See, they are also covalent, right? Okay, ionic bonding model or ionic bond involves the transfer of electron from metal to non-metal to form ions that come together in a solid ionic compound. Simply, one ion become attracted to the other opposite charged ion, right? So the octet rule, when atoms bond, they lose or gain or share electrons to attain a fit outer shell of 8 electrons, right? So that is octet rule. You have already studied. In ionic bonding, the number of electrons lost by the metal atoms equal the number of electrons gained by the non-metal atoms. Right? Usually, the bond occur between metal and non-metal, right? So one loses the electron, the other one gains. So the depicting the ion formation. So sodium, 1s2, 2s2, 2p, 6, 3s, 1, right? 3s, 1. So in s orbital we have 1, in p orbital we have 0, no electrons in p orbital. So what is the common thing? You will remove this electron, right? Here in this one you have 2s2, 2p, O2, sodium plus means you remove this, right? 1 electron. O2, 2 minus. 2 minus means 2s2, 2p6. The ion, right? So oxygen is what? 2s2, 2p, 1, 2, 3, 4. 2p4, right? O2 minus, they gain 2 electrons, so they become 2p6. So what happens is 1 electron from sodium, the other one from again sodium, they gain electrons, right? Because sodium can remove 1 electron from their s orbital, right? So 2 sodiums will lose 2 electrons, whereas 1 oxygen will gain 2 electrons. So that is again 2 sodiums give 2 electrons, so that it becomes 2Na plus O2 minus. So that is N2Na2O, sodium oxide, Na2O. Not visible. Na2O. 2 sodiums plus 1 oxygen. This is the ionic bond or ionic character, right? Again, the same things. Lithium and fluorine, right? Again, lithium loses 1 electron and fluorine receives 1 electron, right? So this one removes 1 and this one gains 1. So they become lithium plus and fluorine minus, right? LiF. Ionic bonding and lattice energy. You can go through this. So the electron transfer process is an endothermic, but ionic compound formation is an exothermic process, right? So exothermic process due to the attraction of oppositely charged ions. So this enthalpy and all that not much needed. Don't bother about it too much. Just get the conclusion what they trying to say. Okay, from this enthalpies. The central point, yeah. Ionic solids exist only because the lattice energy drives the energetically unfavorable electron transfer. Okay, so that is a central point. So ionic compounds, when you break it off, what happened? So when give a external force, what happened to the ionic compound? Because they are in the lattice formation, right? If you see NaCl, all that kind of lattice, right? So they conduct electricity, right? So they have mobile ions. So in covalent bond you don't get a mobile electrons, right? So in ionic bond you get mobile electrons. So that they have passed electricity. And if you compare the what you call melting points comparatively with ionic bonds, it's too high. Usually ionic bonds are more high melting point, right? Metallic bonding, the third bonding, that's all about ionic bonds, okay? So the metallic bonding, the electron C model, all metal atoms in the sample contribute their valence electrons to form an electron C that is delocalized throughout the substance. The metal atoms are not held in place as rigidly as are the ions of ionic solid. So the melting point of the group 1 and 2A elements are given here, right? So see the melting point of group 1 is decreasing and group 2 also decreasing when the down the groups, okay? So lithium has more than francium, right? So what they coming to say, electron C model. So what is electron C? Like metallic bonds, they don't make any ionic bond or covalent bond, okay? They have
Metal and metal.
not metal and metal. Electrons attraction between electron and the nucleus. That is electron C. Okay, electron C model. So when you hammer the metals, they become deformed, right? Not breaks. So that also see how the atoms are deformed. So metallic bond properties, bond formation, electrons are delocalized among metal atoms, right? So occurs between two metals. Type of structure is electron C. Physical state solid except mercury. Melting point very high than ionic bonds. Soluble in water, no, they are not soluble. And electricity conductivity, yes. Other properties, they are malleable, ductile and lustrous, right? So this is the electron C. See, there are delocalized electrons, means like 1, 2, 3. Only up to 3 electrons are there, no? So if you take sodium 1 electron, magnesium 2 electrons, and aluminum 3 electrons, then they tend to become non-metals, right? So they have localized Cs, right? So they have an attraction between the nucleus and the electrons. So that is how they are stabilized. Conduction of heat. Electrons are able to gain kinetic energy in hotter areas of the metal and are able to quickly transfer it to other parts of the metal lattice because of their freedom of movement. Heat causes the electron to move faster and bump it off these electrons with each other and proton transfer the heat. So when the heat is given, they tend to more vibrate. Okay? They spin more. Okay, called vibration. So they kind of conduct the energy by vibrating it. Okay, so the electrons are also mobile electrons. They can move. So they tend to pass the energy. Okay, so that is how they conducting the heat. Same as electricity. When the electric field is applied to a metal, to one end of the metal become positive, the other become negative. So since the electrons are free to move, all the electrons experience force toward the positive end. So the movement of electrons is an electric current. You all know, right? From one place to other place, when electrons are moved, so the current will be passed oppositely, right? Always current passed from positive to negative, right? Electron movement is negative to positive. Okay, opposite. Malleable and ductile. So metals are malleable and ductile rather than brittle as a result of the non-directional nature of metallic bond. The attractive forces exerted by the positive metal ions for the mobile electrons occur in all directions. This means that layers of atoms can move past one another without disrupting the force between the positive ions and the negative sea of electrons. Like when we see the first, there was a diagram, you can see the ionic lattice, when you like tap, they are kind of like breaking off. Okay, so here they are not breaking, they are sliding off. That is malleable. Okay, so they deform, their shape will be changed. Malleable means making wires, right? So kind of deforming. That is how. So mobile electrons allowed to slide by slide. So high melting point. Generally, high melting points indicate that metallic bonding is quite strong, because you all know that metallic bonds are quite strong. So melting points increase with the increase in the number of valence electrons to the sea, since there is a great attractive force between the cations and the electrons, right? High density. Most metals have relatively high densities because the metallic lattices are closely packed. Structure of metals. Electrostatic forces of attraction between the positively charged cations and the negatively charged electrons hold the lattice together, right? So the metal is therefore seen as a rigid framework of cations immersed in a sea of electrons that serve as the cement holding the three-dimensional cation network together. This is the metallic bonding formation. Okay, no, wait. I think I'm explained enough, but still I feel I'm not that explained, because when you guys are physically not here, I can't talk much. I can't explain much. Okay, so I think whatever the things I need to give, I'll explain the slides. Okay, but if you have any clarification, any doubts, you can contact me. Okay, so hopefully see the next week. Okay, if there is a class, there will be whole day class. Okay, so you will be having morning and evening lecture. So the evening lecture will be an exam. So after the exam, I will be explaining the paper, right? So get ready. If you have any problems, let me know. I think I have explained it somehow. So yeah.